Welcome to Module 13, and we call it in the syllabus Basic Cartography and Map Skills. I believe I'm just going to call it Introduction to Cartography and Mapping. So everyone in this class, Surveying 1, is looking to become an engineer of some variety, a land surveyor, or a geospatial scientist or professional, whether it be GIS or whatever mapping field you go into. We're all creating and interpreting maps as we go. Engineering plans are maps. GIS maps are maps. Surveys are maps. So you got to understand, with the history, people didn't just start off drawing plats of property. They didn't even have private property or small plots or tracts. They drew navigation maps, how to get from point A to point B. One of the most, I think one of the most significant and famous maps in our nation's history are the maps that were produced by the Lewis and Clark expedition that Thomas Jefferson commissioned. And so maps are a graphic way to tell a story, to illustrate facts rather than try to describe. There's a big wide river. It's about 500 feet long. It curves around for about 12 miles below the dam. Well, a map might show that exact where the dam is in the map, and then you might look at that and go, oh, there is a very old adage that still applies, and that is that a picture is worth 1,000 words. So a picture or a map, in this case, could describe more about an area on the surface of the earth in one visual presentation than 1,000 words could describe it and still probably not do the job. So in putting this lecture together, what I've done is we're going to go back and hit chapter 17, the first 3 sections, because we're at the confluence of surveys and mapping, and so this is my suggestion to the author to have the sections a little bit more maybe redone. But chapter 17.1, mapping surveys are made to determine the locations of natural and cultural features on the Earth's surface and define the configuration or relief of that surface. Once located, these features can be represented on maps. That's very simple and aptly put. So we think of surveying as boundary surveying precision. If you're trying to draw a map of 12 miles of river to help somebody figure out how to raft it or where to meet you to come out with a canoe, it doesn't have to be to the nearest 500ths of a foot. So mapping is typically low precision, large scale surveying of sorts. Now, if you were to take a large scale map that shows like a whole county and zoom in till you're just looking at one parcel, then you would expect that parcel data to be very precise. But when you zoom out, the parcel gets lost, so it's somewhat irrelevant. So maps typically show railroads, rivers, streets, schools, buildings, towns, anything that can be incorporated to describe graphically the surface of the earth. Now, in the most recent era, say of my youth, maps were strictly paper. Computers were not coming around, and I say that for reference because we're just talking about 30 or 40 years ago. Computers were not something that everybody had or had access to. If you were going to drive across the country, whether if you were recreating, road tripping, or if you were a professional driver, you usually kept a road atlas, which is just a book of maps of each state or sometimes parts of states. And there would be enlargements of cities, and that is how you would navigate your way through a city, is to look at that map. Thankfully, in the era we're in, GIS, or Geographic Information Science, typically using ArcGIS platform GIS maps, do a very similar, nice, wonderful, modern job of creating maps and map features and being able to use layer controls and other, niceties. And just to touch on GIS for a quick minute, main difference between a GIS map and a survey map is metadata. You can actually draw a high precision survey in GIS mapping software. It's just pretty clumsy for that purpose. What it's made to do is to depict a whole lot of information in a little bit of time, and to be able to manage where a water line is, and then also be able to turn on a layer that shows where the water meters are. You could even click on the water meters and it might give you the entire billing history, mailing address, etc. So maps are what in a way holds the world together. Not really, but that's what sort of overshadows how we hold our worlds together. If you think also about our Apple Maps or Google Maps or whatever map or navigation your phone or your automobile uses, it's a map. It's manipulating mapping data. It's not to survey precision, and this is a surveying class, but it's important. I probably would put this closer to the front of the book, I guess, too, because surveys are maps. We're drawing maps. That's why CAD skills are very important, because we need our work product to look like a nice, intelligent, legible map. Now, we're going to sidestep just a minute back into section 17 or chapter 17, and I want to talk just a moment about something that should have been in chapter 17 but it's in chapter 18, and that is a 10. This was discussed briefly at the end of the chapter 17 lecture, but these nice illustrations and information that they're sharing there give us an opportunity to talk about a triangulated irregular network, or TIN. It is a form of a DTM, a digital terrain network. Now, this is a TIN derived from a digital elevation model. That's probably a synonym that they're using for a DTM. That's the image on the left. Notice they are all triangles, just like your contour interpolation exercise. They're all triangles. Triangles are planes. If you think back to 8th grade geometry, 3 points in three-dimensional space define a plane. If you have 3 points, regardless of how they're situated, then you've got a plane. So what TIN and contour modeling does is assume that each one of those triangles is a very close representation of what the Earth's surface does right there in 100 planes, or however many planes those are. When processed, you wind up with a contour map on the right, and you can see the break lines down each side of the road and even in the ditch, where it's not just random grid coverage. And something else that I wanted to talk about while we've got this is, if you look at the this baseline, or this the TIN map, I'm drawing a green line along the edge of the road. Okay, now I'm going to come back and I'm going to plot or indicate I've got a blue point right here on the upper side of the road, and I got a blue point right here on the side of the road. Now, if I was to take in purple and interpolate from blue point to blue point, remember I'm saying that within a foot or less, depending on the contour interval, it is a three-dimensional straight line from one point to another point that we interpolate on. The green line is a break line. We do not need to break across or cross break lines, because let's just say that you've got a shot here in the roadbed, and you've got a shot here in the other side of the roadbed, and you've got this steep slope coming down. If you interpolate from here all the way over to here, you're saying that this is a three-dimensional straight line, and your contours should stack up accordingly. But in fact, if there's this cut and it's level down here, then your contours will be drawn incorrectly. So you have to be careful of break lines. That's something that would be covered in a more advanced topographic class. So here we come to another example of a TIN, a triangulated irregular network. Triangulated is really a misplaced term, but that is the industry standard. A lot of people think it stands for topographic interpolation network. which is actually a better term, honestly. It really does, describe it better. What they've done here is a bold-faced letters indicate triangles, which are those planes. Ones indicate the edges or the sides of the triangle. So this illustration here is an automated auto contouring 10. So if you had, just say you had topo shots at each of these points on the triangle, then it's going to automatically draw a triangle between the points that it's closest to. So like the algorithm would be that it might start over here at 1, or on top of this line 1, and then it's going to say, okay, I've got a line here, I've got another point here, I've got a point here, and then it's probably going to do some kind of algorithm where it jumps down here and it's going to say, okay, I've got a point here and a point here, and then it's going to jump over here and start connecting to the nearest points that it inverses until it creates this 10. That's why I just say if this gray line was a road or some kind of irregular feature, you would need to have additional shots and break lines so that the triangles represented the actual plane. And again, the book doesn't really go in the same order that I probably would, but when we're thinking about maps, the next thing that I believe surveyors especially and engineers should think about is the scale of the map. Now, this doesn't really speak to it. That's more something you would have covered in your drafting prerequisite, but based on contour interval, this is suggested map scales from the book, and we use the English system, so they're saying that if you're drawing a 50 scale map, then you should probably draw your contours at 1 foot. 100 scale map, probably want 2 foot contours, and so forth until you're up at 1,000 scale, and then they recommend 20. I push back on this and say it really depends on how steep the topography is, because you want it to look like the contours flow and speak to you. If you've got a contour on one side of the map and a contour on the other side of the map and it's 20-foot contours, then go to 5 foot or 2 foot or 1 foot contours. If the contour map is just a solid blurb of just lines that are running over each other because the property is so steep, or because you're trying to do a 1 foot contour map at 1 inch equals 200 feet, then go to a larger contour interval. That's just kind of common sense. But what I suggest for surveyors and engineers is to consider how much room you need around the subject area that you're drawing, the property, the contour map, the plans, the detention pond, the bio recharge area, whatever it is, and how that fits the sheet size. Because even if everything's done and submitted and shared electronically, at some point they need to be, if they're done right, so that you can plot them to a scale and it look like it should if it was all paper the whole time. Some agencies and municipalities still require paper submittals. Nothing else, when you meet on site, tablets are nice, but if you're zooming in and trying to pan over to a sheet, that's just not the same as unrolling a set of plans and pointing and taking a pen and making comments and marking up things with people. So always make sure that your scale accommodates what you're doing. In other words, if it's a 1 acre lot and you're putting it on a 24 by 36 sheet, don't do it at 1 inch equals 100 feet. You're going to be about 2 inches square, and 98% of your drawing is going to be blank paper or notes. Don't flood a drawing like that with notes when you're trying to draw attention to the property or the project that you're drawing. You probably want to do that on 1 inch equals 20 and 1 inch equals 30, so that it makes a larger impression and jumps off the page, but mostly so that you can get more detail. If all it is a 4-sided plat of property with no structure, setbacks, contour lines, or anything else, then draw to whatever scale you want to. You don't have any extra detail to provide. But if there's any detail to provide, make sure that your sheet size accents it. And this figure 18.1 is a good example of what I was talking about too. The irregular shape there, the trapezoid in the middle, this shape here, This is what the property of the project is. So unless you've got a good reason, you don't want it shifted over to the left side. They're saying this is the center, the visual center of the drawing. We're going to talk about title blocks and stuff. This is where the visual center is. The physical center might be where the middle of the paper would be if you do a line from corner to corner. But typically if you've got a legend or some title block info, that's going to shift the visual center up some. So what you want is more like this illustration B here, where the legend's all the way across the bottom. The object that you're drawing here, it's centered up in the drawing so that it makes sense and flows. So this is another example. I mean, I'm not sure exactly the relevance, but this is an odd survey document of sorts where they've got these 5 points. It's got a physics building and an annex in the middle. It's got bearings and distances. It's got some coordinates on it. I'm not sure what M is. I guess M, well, I shouldn't say it. M's not necessarily going to have a value, but if you're trying to center the drawing over on the left side, what they're saying is the relevant spacing between objects should be similar on 3 sides. That's really all you can do is on 3 sides because paper is irregular. They're showing a 1-inch margin on the left. That's alluding to when sheets are printed and stapled. You want a larger margin on the left side. They're recommending a 1/2-inch margin on the bottom, the top, and the right-hand side, and that's pretty common. Some places will even have a larger margin than 1 inch because they may use different ways of binding prints. But here's some notes. All bearings reference to geodetic north. It's kind of interesting. All bearings here reference to geodetic north, but they're showing you where the magnetic declination is. Declination 10 degrees west. They should have said degrees, but they're saying that this is the north according to your compass, but yet we're here on the geodetic north. So if you got a compass and you're wanting to go out and find where these points are, you're going to look 10 degrees to the left in order to get dialed in or calibrated to this particular map. Every good drawing or map needs a title block. And here's one that Dr. Galani introduced from 2014. You're typically going to have a scale. We're going to talk about that in a minute. This might be ABC Engineering Company or Chastain and Associates Surveying Company, but here it is, the Pennsylvania State University program. The title should always be in your boldest font and grab the attention of who's looking at it. It would be the project name. If it is the Shoal Creek Wastewater Treatment Plant, that's what you would make bold and center out to speak out. If it's a survey of John Doe's property, then you want John A. Doe to be bold there in the middle. And you'll have a lot of information. The map by this person, the survey by this person. Let's talk about scale. This thing is really odd. What is 1 to 480? Well, you're thinking that just don't understand what 480 is. So part of what we're doing here is we're talking about relative map scales and mapping. So typically what we're looking at in the surveying and engineering world is we're going to draw it at 1 inch equals 30 feet. We're going to draw it at 1 inch equals 40 feet. And what that means is 1 English inch on that drawing surface when plotted at scale is equal to 40 feet on the ground. So if you scale something that's 5 inches long on the paper, then it's going to be 200 feet long on the ground. So a 200 foot long building would be 5 inches long on a 1 inch equals 40 foot scale map. Now, cartographers and mappers, knowing that different people use different scales, they use a ratio, not a true scale. This is a mapping ratio. And they call it in 17.3, they call it a ratio or representative fraction. So this means that basically 1 inch equals 480 inches. 1 foot equals 480 feet. Or let me restate that. 1 inch equals 480 inches. Let's stop there. So 1 inch equals 480 inches on the drawing. Well, how much is 480 inches? It's 40 feet. So 1 to 480 is the same as saying 1 inch equals 480 feet because there's 12 inches in a foot. 1 foot equals 480 feet would be another way to put the scale. We don't do 1 foot equals, we do 1 inch equals. So you would take the 480 and divide it by 12 to get to 1 inch equals 40 feet. So that's another thing that's, like I said, in 17.3, the scale depends totally on what you're trying to depict, how much detail has to be shown. If you're trying to just illustrate that there are 50 states or 48 coterminous continental states and there are some major highways that connect them, you might do that on 1 inch equals 2,000 feet or 1 inch equals 500 miles and get it on letter size paper. But obviously that's not going to work if you're trying to show more detail for some other purpose. Here's the way that typical graphic scales are shown on surveys and maps. It's pretty simple. You say this is a 1 inch equals 50 scale. Then it's saying from 0 to, from here to here is 50. Here's another 50, which totals 100. Here's another 50, which totals 150. Or this is 100 miles. So, somewhere in here is 50 miles. Somewhere in here is 25 miles. Meters, it could be feet, but on the 20, this would be 5, 10, 15, 20. That's just typical, just understanding the scale of the maps. So this leads us into, this is a snippet from the USGS Blue Ridge Quadrangle map. And you can see a few things should jump out at you, and I'll explain what some of it is. You see these contour lines. You've got a high point here on Horsepen Mountain. It's 3575 feet above sea level. It tells you a whole lot right here. Contour interval, 40 feet. Notice what's in big and bold. Scale, 1 to 24,000. If you do the math, that's 1 inch equals 2,000 feet. So, this is where, on the drawing from here to here is going to be 1 inch because it's 2,000 feet. Due to different, metric conversions and initiatives, it's got, it's got a kilometers scale. From here to here is 1 kilometer. So you could use this map in metric or feet, and it's the same proportion. It's 1 to 24,000. They're stating here that this map complies with national mapping accuracy standards, which we will touch on briefly. And this shows us some detail. It shows us that we're right here up near the North Carolina border in the northern part of Georgia. And then they have this key map. So we're the map in the middle. If you're wanting to find the map that's to the northwest, it is the Epworth quad map. If you want to see the map to the north, it's the Mineral Bluff quad map, and so forth. The map to the southwest here, number 6, is the Ellijay quad map. So they name those, and they have different numbers that help to keep things simple. On each of these around the border, you'll see various ticks, which we'll speak to in a minute. And this is 17 degrees, 30 minutes within whichever quadrangle. Quadrangle means that it's 15 minutes, which is a fourth of a degree. So 4 of these quadrangle maps side by side equals 1 minute of longitude and 1 minute of latitude. Thankfully in the US, those are roughly square or rectangular, and we're able to have nice looking square maps or square-ish maps. Obviously, if you get to closer to the North Pole, they're very skinny and very tall. And if you get down near the equator, they're almost perfectly square. But that's a degree of latitude tick. And I'll erase that so that it can be seen a little bit better. And these others are ticks for various coordinate systems. For right here, we're Zone 749, Zone 747, 48 may correspond with 17 minutes 30 seconds west longitude, or it may be that they just didn't want to show the 48 tick mark because of that. And it's not got to do, these lines in the background are actually landlocked lines that have been transposed to help navigate where people are and identify property lines. And in the USPLS states out west, mostly, and in Florida, these are township sections and ranges, not landlots. But these are grid ticks if you're looking at a projection in UTM or Universal Transverse Mercator. That's going to help you figure out where you are. Of course, now with GPS capabilities on the fly, mapping skills are a lot less important because it will plot you exactly where you're at. And you can look and zoom in and out and see where you want to go. But it all relates back to the data that started out on a printed map that we're now looking at going down the road. So on maps, cartography is the art of drawing maps, and it is an art. There are systems and things that we look for even on digital maps today that all tie back to the original USGS mapping program, and I have included some excerpts from their mapping symbols publication, which is part of your handout this week. And so we'll start with buildings and related features. A building, it's shown, in like a square or a shaded in box or something. Also, a school or a house of worship is drawn the same way. An athletic field is typically hatched this particular way. A built-up area, forest headquarters, and this has cut some of this off. Unpaved landing strips, dashed lines. These are landing strips that are more solid lines. Coastal features. Again, there's a lot more in the handout, but I'm just hitting on some of the high points. They've got an exposed wreckage. I think that's pretty neat. A group of rocks, bare or awash. That would be boulders the size of houses to show up on quad maps. But they might label reefs, mud flats. A seawall might be drawn this way. A pier is going to be drawn like this, where they've got the pier walls. Contours. We've been talking about this. This is great. Notice that here the index contour is bold and has the contour label in it. This may be out in Colorado somewhere. It's a 6,000 foot contour line. Approximate or indefinite contours are going to be shown in dashed lines. That's where, for whatever reason, they didn't have good data. This is mainly what you'll find on very old maps, because in the last 60 to 80 years they've fixed all that. But if you run across an old map, which often in land surveying we have to go back to maps from as far back as 100 years ago or more to try to determine where roads were at the time, or where traffic patterns connected in the early days of cars, or where property was identified as cultivated, or any multitude of things that may be lost now. That may be our best evidence. Contour line and intermediate contour line, it's a little bit lighter, a little bit smaller than the index line. It does not have labels. Just label the contour interval. Supplementary, so like if it's a 10-foot contour and they want to show some fives, it'll be very faint. And I just covered over that, but it'll be a lot fainter than your intermediate, to let you know. And typically what we actually do, these are for quad maps, because dashed lines they imply uncertainty. But when we're preparing topographic maps to where uncertainty is not an issue because we have good data, we'll typically do dashed lines just because solid lines tend to overpower or overstimulate the drawing. And there are other solid lines on the map that they conflict with, such as property lines or setback lines or buildings. And here's a depression. You remember we got the tick marks that point to the low spot. Controlled data and monuments over on the right. This is how they will often, if in their process they're running across a third order or better elevation boundary monument, they're going to call it benchmark and say it's at elevation 9134. Or this other symbol, they use different symbols over the years. And they're just showing you here, these are some of the symbols that you'll run around or run into. You know, a third order horizontal control is going to be a triangle with a dot. If it's got an elevation, well, then it's going to have an elevation next to it, probably a tick mark in the middle. Projections and grids, we were just talking about at the corner of this, you know, the quad map they're using here. You know, the bottom of the map is going to be 39 degrees, 15 minutes. So the top of the map is going to be at 39:30. It's going to be 15 minutes or a fourth of a degree up. If this, you know, the right edge of this map is at 90:37:30, then this over here is going to be 15 minutes more, or 90:37:45. So that basically at the end, you know, this is how a whole 1 degree of latitude would be illustrated. And so if you get a larger scale map instead of being a quadrangle map, it may show a whole degree of latitude and longitude like this, which would have a total of 16 quadrangle maps drawn inside of it. And that's kind of bad, but you get the idea. And we were just talking about this. Primary zone tick, secondary zone tick might have a dashed line here instead of a solid line vertical. A intermediate or tertiary zone tick, a quaternary zone tick. That, you know, if you were doing a lot of orienteering or navigating out in the woods, this would be very important. And here you're looking at, again, we're talking about the UTM full grid. If you're there, that's going to be a solid line. What we were seeing is grid ticks, where you're at zone tick or tick 2 of zone 69. Railroads, typically a line with a dashed, you know, multiple track. You're going to have 2 of them. Narrow gauge railroad, which you might see in mining communities where they're not the big railroads that they haul freight and passengers on. They're going to have a line on one side, then a line on the other side, and so forth. Multiple track narrow gauge will be just 2 lines. Side rails, where they pull off for loading, are drawn like that. Various different things that we could talk about. A rail yard is going to look something like this, where the lines split off and they park trains, you know, by the gazillion. USGS mapping symbols continued. Roads and related features. You know, these are in color, which our maps are not always in the surveying world or the engineering world, although we have the capabilities to. A lot of times they're going to be duplicated and scanned in black and white, so we might be staying away from color. But, you know, primary highway is a large solid line. A secondary highway is a colored large line with with the interior dashed. Light duty gravel, light duty dirt, unimproved road, 4-wheel drive road, trails, single dashed line. Over here on the right, rivers, canals, and lakes. Now, one thing that is really not brought out here, because in large scale maps you don't see it, but when we're drawing topographic maps and surveys, streams are typically a triple dot line, like they've got over here for intermittent. So it's what they've got. You know, if you look at it here, intermittent stream, an alternative. You know, solid line or solid stream is going to be blue, as same as in a perennial stream or perennial river. They're going to be blue because water is known as blue, and they're going to be solid because, just like with contour lines, doing any kind of interruption says it's not as important or it's not as accurate. So that's why intermittent water features on large scale maps have the 3 dots in the line type. But whereas in surveys and maps, that could very well be a river. I think it's pretty neat here. They've got, you know, small rapids and large rapids. You know, the one on the right in the lower right hand corner right here, it looks like it must be a you know, set of waterfalls worthy of whitewater rafting. Also, for water features, you know, ponds are going to be an enclosed circle because it's going to be the surface of a pond or lake. Intermediate, they're going to do something dashed in between to let you know. If it's dashed, it's going to, or if it's dry, it's going to be, looks like a red or a pink, or just labeled as a dry lake. And you have a lot of those out west where, you know, they only get water in them certain times of the year. Also showing water wells, geysers, mud pots, things that we don't have in the southeastern U.S. a spring or a seep. If there's a big noticeable spring where water comes out, you don't see this much in the southeastern U.S., but they do exist. On the right, submerged areas and bogs. This is swampy. You've got the swamp symbol for a big marsh. If it's submerged, it's going to have blue around it like a water. It's like like the Okefenokee Swamp's probably going to look like this because it's submerged. If it's wooded, they use this symbol. They use different symbols. Land that's subject to inundation, if they can tell when they're preparing the map that this area gets flooded fairly often, but it's not always flooded, or maybe it's a big holding lake where they discharge nuclear water around nuclear reactors. Sometimes they'll issue out or drain the hot water into a lake to let it cool off, or they'll cycle it out and bring cooler water in. So when they're not doing that, it's going to be a big dry hole in the ground, and then when it does fill up, then it's going to be full of hot water. Again, this is mapping. They talk about this here early in chapter 18. This is where you would go out and have check shots throughout the map, and this is not on a 1 acre site or anything small. This is where miles apart sometimes you would check positions and see how close they are to where they scale on the map. The map probably would be generated from aerial photographs or various cadastral or just planimetric or topographic ground surveying over the years. Maps started before you could get aerial views much, but little known fact, they did use hot air balloons in the Civil War for reconnaissance and navigation, and they quickly figured out that that is the best way to draw maps. Wow, if Lewis and Clark had only had those 40 years earlier, 50 years earlier, wow, they could have done such a much better job and covered so much more ground. So, from there, then the airplane came along several years later. But a lot of aerial photographs up until around World War I were taken from hot air balloons or even large blimps that were similar to hot air balloons. But this is just a worksheet that they've provided, which includes elevation data. This is where you would look at this particular point on the map, see where it shows to be, survey checkpoint coordinates, and you'd have this comparison. Here's your delta or variation in this other chart. We're not going to do this. This is just to illustrate how they've done 5 checkpoints. Average mean square is in here, and so the average 95% confidence level is within half the contour interval, or within like 3% of the map scale horizontal, so it would pass. These are things you needed to know about mapping. Please read the book, the chapters or the sections that are assigned, and understand how the pieces fit, because this is surveyors and engineers make maps. That's what we do. So that concludes this lecture. Thank you very much.